welcome back to our channel. Today, we're diving deeper into the fascinating world of curve fitting with a new micro tutorial. Curve fitting is a crucial technique in data analysis and machine learning, enabling us to model relationships between variables and make accurate predictions based on data. By fitting a curve to a set of data points, we can uncover underlying trends, understand the dynamics of the system, and make informed decisions. In this tutorial, we will explore how to determine the best function to describe a given set of data points. Specifically, we will examine three types of functions: linear, exponential, and power. Each of these functions can provide a different perspective on the data, and choosing the right one is essential for accurate modeling and prediction. Curve fitting is important for many reasons. Fitting a curve to historical data allows us to predict future values with a certain level of confidence. Understanding variable relationships aids in identifying patterns and making informed decisions. Optimization based on fitted models is essential in many engineering and scientific applications. A well-fitted curve offers a clear visual representation of data, simplifying the communication of findings. In this tutorial, we have two different sets of data points x and y. Our mission is to determine the best mathematical function to describe the data. We will analyze three types of functions: linear, exponential, power. For each data set, we will fit a linear function. Linear functions are simple and intuitive, providing a clear starting point for fitting curves. Fit an exponential function. Exponential functions are well suited for data that shows consistent growth or decline. Fit a power function. Power functions are effective for capturing data with relationships based on multiplication. We'll plot each function on the same graph as the data points to compare their fit visually. We'll also add labels and adjust the formatting of the graphs to enhance readability, making it easier to see which function best fits the data. Here is step-by-step breakdown. Prepare the data, load the data points, and create initial plots to understand their distribution. Fit the functions. Use Matlab to fit linear, exponential, and power models to the data. Plot the results. Overlay each fitted model on a graph with the data points, and include labels, titles, and legends for better clarity. Evaluate the fit. Compare the fitted models to identify which one best captures the underlying data trends. In order to evaluate the fit, the first measure is taken with the following formula for the total sum of squares represented by ST, where y bar represents the mean of the y data. Secondly, we will calculate total sum of squares of residuals represented by SR. In this equation, y fitted refers to the data values predicted by the respective curve. Lastly, we will approximate R squared. R squared quantifies the proportion of the variance in the dependent variable y that is predicted from the independent variable x. R squared equal to 1 indicates model perfectly fits the data. R squared equal to 0 indicates model does not explain any of the variance in data. So, in order to select the best model, we will compare R squared values and select the one that has highest value of R squared. Let's get started with Matlab and see which function provides the best fit for our data. Print if linear fit is the best. Print if exponential fit is the best. Print if power fit is the best. End of the function. The print best function takes in the R squared values and determines which model has the highest R squared value. It then prints the best fitting model. The fit curve function fits the data to linear, exponential, and power functions. It calculates the R squared values for each model and plots the original data along with the fits. Fit the data to a linear function. For the linear fit, we use polyfit to find the coefficients and polyvol to evaluate the fit at the data points. Fit the data to an exponential function. For the exponential fit, we take the natural log of the y data, perform a linear fit, and then transform back to the exponential form. Fit the data to a power function. For the power fit, we take the natural log of both x and y data, perform a linear fit, and then transform back to the power form. Calculate R² values. Calculate total sum of squares. Residual sum of squares for linear fit. Residual sum of squares for exponential fit. Residual sum of squares for power fit. We then calculate the total sum of squares and the residual sum of squares for each model to determine the R² values. Finally, we plot the data and the fits on a graph. Plot the data and fits. Turn on grid for better visualization. Add legend function. Label x-axis. Label y-axis. Add title to the plot. End of the function. Next, we move on to part A. We define our data points. We create a new figure window and call our custom function fitCurve to fit the data and calculate the R² values for each model. We then print the best fitting model. we can observe that the r-squared value of linear fit is 0.9919, whereas r-squared value of exponential fit is minus 1.2956, and it is minus 0.7176 for power fit. This shows that the maximum value of r-squared closer to 1 is achieved by linear curve fit. It is noticeable from the figure 2 that the linear fitting curve passes through all the data points, thus modeling the data points better than other two curve fitting models of exponential and power fit. Next, in part B, we define our data points. We create another figure window and again call fit curve to fit the data and print the best fitting model. In part B, we can observe that the r-squared value of linear fit is 0.8583, whereas r-squared value of exponential fit is 1.9407, and it is 0.9985 for power fit. This shows that the maximum value of r-squared closer to 1 is achieved by power curve fit. It is noticeable from the figure 2 that the power fitting curve passes through all the data points, thus modeling the data points better than other two curve fitting models of linear and exponential. Finally, in part C, we define our data points. We create one more figure window, called fit curve, and print the best fitting model. In part C, we can observe that the r-squared value of linear fit is 0.8420, whereas r-squared value of exponential fit is 1.9998, and it is 0.9955 for power fit. This shows that the maximum value of r-squared closer to 1 is achieved by exponential curve fit. It is noticeable from the figure 2 that the exponential fitting curve passes through all the data points, thus modeling the data points better than other two curve fitting models of linear and power fit. We have seen in this tutorial that all the three data sets were suited for different type of curve fitting models. It is observed that part A dataset was best modeled by linear fit. Part B dataset was found its best model in power fit, and Part C chose exponential fit as its best model. Thus, we learned today about curve fitting techniques, and we also learned how to choose a mathematical model for our dataset. If you enjoyed this tutorial, remember to like, comment, and subscribe. Thanks for watching.